Imagine your neighborhood. It's a brand new development, and all the houses are built, but there's a problem. No internet. Catastrophe, I know. A cable company has been hired to connect all the houses with high-speed fiber optic cable, but they have a very specific goal: use the absolute least amount of cable possible. Wasting cable costs money, and in business, wasting money is a big no-no. They can't just run a main line down the street and connect each house individually, because the houses are scattered all over the place, on cul-de-sacs and windy roads. They need a network, a single connected web that reaches every single home. So how do they solve this puzzle? They could just start digging trenches randomly, but that would be messy and incredibly inefficient. They could connect the two furthest houses first, but that might create a super long, awkward line that isn't ideal for connecting everyone else. This is a classic optimization problem. It's not just about connecting everything. It's about connecting everything in the smartest way. The goal is to create a network where every house is on the grid, but the total length of all the cables combined is as short as it can possibly be. This ensures everyone gets their cat videos, but the company doesn't go broke buying extra cable. This exact situation is a perfect real-life example of what computer scientists call a minimum spanning tree problem. Think of the houses as dots, or nodes, and the possible cable paths between them as lines or edges. Each of these potential paths has a cost associated with it. In this case, the length of the cable needed. At its heart, Prim's algorithm is what we call a greedy algorithm. No, it doesn't hoard all the snacks at a party. In computer science, greedy means that at every single step of the process, the algorithm makes the choice that looks best at that immediate moment. It doesn't worry about the grand long-term plan. It just focuses on making the most optimal, cheapest, or shortest move available right now. And it trusts that all these small, smart choices will add up to a brilliant overall solution. Let's get practical. Imagine we're not connecting houses, but famous landmarks in a small town: the library, the school, the park, and the cafe. We have the costs, let's say the length of road to build, to connect each of them. Our mission is to connect all 4 landmarks with the least amount of pavement. First, Prim's algorithm says we have to start somewhere. It doesn't matter where, so let's pick the library. The library is now our starting point, the first member of our connected network. It's a lonely network for now, but it's a start. This is step 1, pick a starting node. Now for step 2, the greedy part. We look at all the possible connections leading out from our current network, which is just the library. Let's say the connection from the library to the school costs $10, and the connection from the library to the park costs $15. Which one is cheaper? The school, of course. So we greedily choose that path. We build the road from the library to the school. Our network has now grown. It contains both the library and the school. For step 3, we repeat the process. But now we look for the cheapest connection from any landmark within our growing network to any landmark outside of it. Our network currently includes the library and the school. We check all possible outgoing paths: library to park, which costs $15, school to park, which costs $4, and school to cafe, which costs $8. We look at all these options and ask, which one is the absolute cheapest? The road from the school to the park for just $4 is the clear winner. So we build that road. Our network now includes the library, the school, and the park. We're almost done. For our final step, we repeat the process one more time. We look at all the connections from our current network, library, school, park, to the one remaining landmark, the cafe. The options might be school to cafe for $8 or park to cafe for $12. The cheapest choice is the $8 connection from the school to the cafe. So we build that. And voila! All 4 landmarks are connected. We have a network, a minimum spanning tree, and we found it by always making the cheapest possible move at every step. We never had to second-guess ourselves. It's fascinating to compare Prim's methodical, greedy approach to how a human might try to solve the same problem without a set of rules. If you were handed a map with a bunch of cities and asked to connect them with the shortest total road length, your intuition might, honestly, lead you astray. For instance, a very human thing to do is to try to connect nearby clusters of cities first. You might see 3 cities bunched together in the north and connect them. and then 2 cities in the south and connect them, and only then figure out how to bridge the 2 separate networks. This is known as a bottom-up or clustering approach. The problem with this human-centric strategy is that the final connection between your 2 pre-built networks might be extremely long and expensive. You might end up with a very inefficient trunk line because you committed to your local connections too early. Prim's algorithm avoids this pitfall entirely. It never works on separate, disconnected pieces. It grows a single, contiguous tree from the very beginning. By always expanding one connected network, it ensures that it's always considering how the whole system is growing, not just isolated parts of it. It prevents you from painting yourself into a corner with a costly final connection. This highlights a key difference between computational thinking and our everyday problem solving. We humans are great at seeing the big picture, using heuristics, and making educated guesses. Algorithms like Prim's, however, thrive on rigorous, step-by-step logic. They don't have intuition, they have instructions. So why does any of this matter outside of a computer science classroom or our imaginary cable company? Well, because the world is literally built on networks, and making those networks efficient saves time, money, and resources on a massive scale. Think about the power grid that brings electricity to our homes. Engineers designing the grid need to connect every substation and transformer, using the minimum amount of expensive high-voltage cable. Prim's algorithm is a perfect tool for designing that layout, ensuring reliable power without wasting millions on unnecessary infrastructure. The applications don't stop there. Consider designing a water pipeline system for a city, laying out telecommunication networks to connect remote areas, or even planning airline routes to ensure a carrier can service a set of cities with the minimum total flight distance. It's also a powerful tool in the digital world. When you're playing a video game, the game's AI might use an algorithm like Prim's to calculate the most efficient path for characters to move through a complex environment. In all these cases, you have a set of points that need to be connected at the lowest possible cost. Even in biology, scientists use similar principles to understand how things are connected, like mapping out clusters of genes or analyzing molecular bonds. The fundamental problem of efficient connection is everywhere. Ultimately, Prim's algorithm is a beautiful lesson in problem solving. It teaches us that by breaking down a dauntingly complex problem into a series of small, manageable, and logical greedy choices, we can arrive at a perfect, optimal solution. It's a testament to how a simple, elegant set of rules can create order and efficiency out of chaos. From the internet cables under our streets to the power lines overhead, the principles behind Prim's algorithm are quietly and efficiently connecting our world, one logical, cost-effective edge at a time. And that is pretty amazing.